Hi there, in this video we're going to look at the Fourier transform of a delayed function both in time and in frequency. So we've already seen something similar to this when we looked at the impulse function. Now the impulse function can be written as delta t, and we know the Fourier transform of the impulse function is 1. Okay, so graphically we looked at that and we said if that was t and that's some function of t and the function of t is the impulse function there, then the function of frequency, so that's of j omega, is equal to 1. That heads off to infinity in both directions. Okay, height 1, that's f of j omega. Now if we can think about this kind of digital at the moment, if we are discrete, think about this as rotating phasors. Okay, obviously it's continuous, but I'm just drawing this out just so you get an idea. Okay, so that's the Fourier transform of delta t. Now if we find the Fourier transform of delta t minus t naught, so here's a function, there's, let's say that's t naught there. Now that's our time axis, that's f of t, and that function there is delta t minus t naught, so we've got a delayed impulse. Now you've seen from one of the previous videos that the Fourier transform of that, well, when we shift it in the frequency, it's equivalent to allowing all the phasors to start rotating. Okay, so it means that this phasor here can start rotating this way, and this one will start rotating, and these ones can rotate as well. So you might have something along the lines of this here. Okay, so you can see that the phasor starts to map out, okay, a 3D line. Okay, so you can say that's j omega, f of j omega. Okay, and it turns out from our analysis, which we did in the previous video, that delta, fix this just now, Fourier transform of delta t minus t naught was e to the minus j omega t naught. Okay, so that's equivalent to adding a phase shift into each of the phasors, or a overall phase shift of the original function, delta t. Okay, so the same sort of thing occurs with functions. So we're interested in the Fourier transform of a delayed function in time, so t minus t naught. Okay, so to find that, we just go through the Fourier transform. So that's integral from minus infinity to infinity of the function times e to the minus j omega t by dt. Now if we replace t minus t naught with a value tau, then we can say that the value t will equal tau plus t naught, and we can say that our dt will equal d tau. Okay, so if we go ahead and we replace each of those, then we'll get the integral from minus infinity to infinity of f of tau times e to the minus j omega, and it will be tau plus t naught by d tau. Okay, so what we can do then is we can rewrite that there, and we can take out e to the minus j omega t naught, because we're integrating with respect to tau and not t naught, so t naught is independent of it. So we can say e to the minus j omega t naught times the integral from minus infinity to infinity of f of tau e to the minus j omega tau by d tau. But as we see here that we're going to be left with e to the minus j omega t naught. Well, this is just the Fourier transform, okay? So we could just rewrite that as f of j omega. Okay, so it means that we're left with the, if we have a Fourier transform f of t and the Fourier transform is f of j omega, then what we can say is the Fourier transform of t minus t naught is equal to e to the minus j omega t naught times f of j omega. Okay, so that's our little transform pair there. That's one we're looking at, this one here. Okay, so we can, again, we could draw that function out as well graphically. So we could say if we had a, let's say we had a sinc function. Okay, so we know the sinc function there will look something like that. Okay, I'll just draw the little lines in representing that. Okay, and that's a function of t, and that's f of t. Now we know when we find the Fourier transform of that, we'll end up with something that looks like square wave. Okay, now when we delay that sinc function, write down a bit, when we delay that sinc function, so we take a copy of that sinc function, but it's a delayed version, delayed in time, that'll look like that. Okay, that just has the effect of adding a delay onto these, okay, adding, sorry, phase onto these, so you're just going to end up with something that looks like that there. Okay, so instead of having that straight edge there, it looks like in 3D it looked like a curve. Okay, so what happens is it ends up with a real and imaginary part. Okay, so that's all there really is to say about the delayed impulse. I suppose I could add in, sorry, I'll finish off and say because of the Fourier transform, we looked at the Fourier transform surface and it's purely symmetric, so we could say if we had a function of frequency j omega and it was delayed by some value omega naught, so we put in j omega naught, okay, then in the time domain that would be equivalent to taking the signal in the time domain, okay, f of t, and adding a delay, adding a phase into it of e to the minus j, well not minus, that would be going to plus j omega naught t. Okay, so that there is our other transform pair. Okay, so all we're saying is rather than taking, if we redraw this one here, if we let's see if we can get it in this one here, if we were to take a delayed square wave, okay, so if we delay that, so it's over here somewhere, okay, so we've now delayed it by some value omega naught, then in the frequency domain that would have been, that's equivalent to a sinc, but in the frequency and the time domain now we would have a function, okay, that would look similar to the sinc function, but all of the phasors would be delayed. Okay, so we would have something that would, although it's difficult to draw, but all these phasors would come out, so at different angles. Okay, so we would have some delayed. So we have some curve, okay, but all the phases are delayed, so it ends up we have some three-dimensional curve. Okay, so that's all I have to say there. Again, I'll intersperse some of these videos with some examples of where we can use this, but that's all for now. Okay, so thank you and goodbye.